Okay, so now we're going to do problems 5A through C from section, which are some AVL runtime questions. So question 5A asks us to find the type Big-O bound for the worst case insert and find in a BST. So the first thing to do when you think about when you see a problem like this is to figure out what a worst case BST might look like. So in the worst case, we'll end up with a linked list like tree. And the way that we can create this is by inserting elements in sorted order. So like 1, 2, 3, 4, 5, 6, 7. Because if we insert it in sorted order, that means that every single node that gets added is going to add one level to our tree. So this means that our height of our BST could potentially be n because we're incrementing height every single time we do an insertion. So if we do an insertion, then if we want to think about the runtime in the worst case, we could potentially insert an item that is at the bottom of the tree. So this will require us doing n iterations to get to the bottom to actually find the place to insert. So this ends up being an O of n operation. For our find, if we're looking for our biggest or smallest item, depending on how you insert your tree. So if you did 7, 6, 5, 4, 3, 2, 1, everything would be on the left side. Your item could potentially be the very last node in your tree at the very bottom row, and because your height is potentially n, this will also end up being an O of n operation. So those are both the answers for this problem. The next question asks us to find the worst case for insert and find in an AVL tree. So we can think about what our worst case AVL tree is. So it turns out that our worst case actually isn't that bad. So one thing that we know about AVL trees is that they're balanced. And because they're balanced, we can guarantee that they have a height of log n. So when we're trying to insert something, we need to insert it at the bottom of the tree, which means that we'll have to do log n iterations to find where to insert it. So we'll have to do log n iterations to find where to insert it, and then fixing the tree and potentially restoring balance will also take log n. So this ends up being an O of log n operation. So with find, we only need to actually find the element. So potentially it's going to be at the bottom of our tree, which has a height of log n. So this is also going to be a log of n operation. Alrighty. So the next question asks us to find the worst case for finding the minimum value of an AVL tree containing n elements. So this is kind of an interesting problem. So we should first figure out where the minimum element is going to be in our AVL tree. So the minimum element must be the very leftmost item of your tree. So in this example, it's 25. We know that it can't be anything except for this leftmost element because if there's something to the right of this 25, it has to be greater by definition. And if there's anything further left, then we would have chosen that. And it definitely is not 50 because if we were to go left on 50, we'd find something smaller. So your minimum element is going to be the very left of your tree. And potentially this very left element is going to be at the bottom of your AVL tree, which means that if we want to go to the bottom of our AVL tree, we know that the height of our tree has to be about log n. So height of our tree is going to be bounded by O of log n, which means that our worst case for our find is also going to be O of log n. And that's the answer for this problem.